there are several different probes that are reasonable to use in our system. I think there's 5 or 6 manufacturers now of probes. Most of them are owned by Nano World now. Like Micromash used to be independent, Budget Sensors used to be independent, Nano Sensors used to be independent, but they're now owned all by Nano World, which I think is still owned by Manfred Dieterbeck. But you'll see tons of different kinds of probes. Generally speaking, you have a class of probes called contact mode probes that are made of silicon nitride. They are either beams, like a standard cantilever beam, or they're triangles, so they're two-legged triangles. Initially, they thought that those two-legged triangles would be more stable than the beams. That turned out to be wrong. But because of tradition, a lot of people still use them. They're not bad, they're just the wobbly, you can get some weird wobbly behavior with them. So, but the point is that silicon nitride levers, in general, are considered contact mode levers, or tapping mode levers in fluid. And remember, tapping mode and AC mode are the same thing, okay? Silicon levers, or quartz levers, there's several other kinds of levers out there, but the vast majority are silicon, are generally considered to be tapping mode levers. Right? Now the exception to that is you have this class of levers right in the middle that can either be contact mode or tapping mode. So, contact mode levers are generally less than 1 Newton per meter. Generally. Tapping mode cantilevers for biological samples in fluid are also less than 1 Newton per meter. And again, both of those classes are generally made of silicon nitride. Okay? Above 1 Newton per meter, to about 25 newtons per meter are, well, let's separate it one more way. About 1 to 5 newtons per meter, or 1 to 10 newtons per meter, that's considered intermediate stiffness. And that's going to be for polymers, for, you can use them for DNA, you can use them for proteins, you can use them for viruses, for bacteria, but anything that's dried in air, any biomaterial or polymer material that's dry and in air, those probes from say 1 to 10, that's a good range. Right? Now the resonance frequencies could vary from 50 kilohertz all the way up to 150 kilohertz. Right? There's varying. The resonance frequency doesn't really matter, except that it determines your imaging bandwidth. Right? So if you pick a cantilever that has a resonance frequency of 50 kilohertz and it has a Q factor of 500, you have a very small imaging bandwidth. So you're going to have to image really slow, right? So in terms of the resonance frequency, a lot of times people will classify them by, oh, that's a 70 kilohertz lever, or that's 100 kilohertz, or 300 kilohertz. It's better to think in terms of spring constant, right? So think of below 1 as being contact mode or fluid tapping. Think of 1 to 10 as being intermittent. Think of 10 to say 100 as being tapping mode on very hard surfaces. Silicon nitride, silicon dioxide, gallium nitride, aluminum nitride, hard materials, oxides, right? Diamond, sapphire, mica, graphite. Really hard materials, you can go really high stiffness, right? In general, whatever the stiffness, whatever the spring constant of your sample is, you want your probe to have close to the same spring constant. And there's ways in the literature, there's ways on the internet that you can take the modulus and convert it to a spring constant with a quick formula to get a rule of thumb, right? So, again, if you have specific questions about specific samples, you can either ask the forum. If you join the forum at Asylum Research, lately I've been answering probably 70-80% of the questions on there, so you're going to get me anyway. But there's also some other people, there's users that will answer, there's some software people that will answer. It's also searchable. So there's a lot of data, or there's a lot of information that I've put in there that you can just search, and then you're here at midnight, you can get the data without having to text me at midnight, which some people do. It's fine, I don't care. I just ignore it. All right, so so what I'm going to do is I'm going to load just the calibration. Did you find, Chris, did you find the calibration grating?
There's
There's one here?
There's one of those 1x1 gold ones.
Oh, that's fine. Yeah, that'll work. It doesn't really matter. You just need something to image, right? Initially. So let me find a little fancy sample folder. So the samples that you guys saw during my talk, where they're on those little pucks, I would highly encourage you to mount your samples on those, because there's a little adapter here that lets you image it very easily. It's already got a magnet on it. It's already got kinematic mounting. So it's a nice, simple way to do it. If you do need to put it on glass slides, that's fine. But keep in mind, when you take a glass slide and put it on this scanner top, there's always a chance that the corner of the glass slide is going to break off, and eventually those corners are going to end up in the scanner, and you're going to have downtime, and it's going to cost money to ship it back. So in general, if you don't need a glass slide, I recommend using this with those pucks. You can get the pucks at Ted Pella, right? Yeah. They're, I don't know, 10 cents a piece. It's peanuts compared to that. Again, mount it with super glue, with epoxy, with APAs on wax, with nail polish, with first contact, something stiff, or silicone vacuum grease if you need it removable. Okay? So that's that. Then we find the calibration grating. This is probably dirty, but it'll be alright. Glasses. This is not the standard grading, but it should work. Getting old, I can't see anymore. So the this one right here. All right. Close enough. This happens to be coated with iridium, but so the tip radius is going to be a little bigger than normal, but it'll work. It's the same class of tips.
I have some more tips here.
190, 10, 300. No, this one's better. 75. That one's good. I'll just use mine. But this is an example of the ones I talked about that have an intermediate range. See where it's 3 newtons per meter, about 75 kilohertz. That's sort of the moderate. If you're just doing tapping mode, this is good for almost any sample. If you're doing stiffer samples, then you use the ones like he has, the 300s.
Okay.
Yeah. I'll just use these. So the idea is to take this little block, just helps you steady your hand a little, and you'll drop this drops into here like that. It's supposed to hold it firmly. For some reason it's not. The spring might be dead. Yeah. So now the it's the wrong side. Yeah, I encourage people to do it in a stereoscope. They're less likely to damage it. That's the wrong screwdriver. Is the right one here? Oh, no, that's right. Yeah, that's right. I got one. I think I left it at the hotel room. I have the official screwdriver in my bag. I'll bring it tomorrow. But this is the right size. That other one there was too big. So what'll happen is over time you'll round out. You can already see this is starting to round out because it's the wrong one. So yeah, this is the right one though. So you're going to loosen that all the way up. Just not so that it's getting ready to come out, but just so that it's not tensioning down the clip. Okay, so I back that away. And then pushing motion is generally not comfortable. Think about how your hand feels if you're pushing something away. You're not very strong and you're not very coordinated, but pulling, that's what we do, right? So in general, I recommend using a pulling motion to load the probe. So what I do is lean my hand forward, give myself plenty of angle. Oops, I dropped it. Do as I say, not as I do. Things are a little stiff. So then you're going to pull it in like that. Okay? Now, before I do this, okay, I want everybody to look at this holder. And what you're going to notice, I'm going to hand it around. I'm going to describe it first. You have this larger circle, okay? But then you have this little trapezoid here.
Yeah.
The little trapezoid is the active region. That's where the camera looks through. That's where the laser shines through. That's where the reflection goes back. That is the active part. If you look on the back side, which you don't have to now, but I want you to see, that's the other side of it, okay? Now, the probe itself, if you take that little trapezoidal shape, the probe itself needs to be in the upper half of that. In other words, away from the clip. If you put it too far down in, then you won't be able to align the laser because it'll put it at the wrong angle. So you want it to be out on the end here, right? Not down on the base. So everybody look at that and understand that I'm handing it to you this way. Keep it this orientation. You want the probe to be a little bit up, not pushed down. Okay? So everybody just glance at that. So you see the window that I'm talking about. So it has to be in the upper region, like that part of it. Otherwise the probe will come down. What'll happen is it'll come down, there's a little shelf that's supposed to block it, but what it'll do is it'll ride up on that shelf and then flatten out. And you'll be able to see the probe in the camera. It'll look like everything should work, and yet you won't be able to get a reflection off the back of the cantilever. Okay, so I'm going to load it, and then you guys can all look at it again. So again, I go this direction. Once you've loaded that in and tightened it down, and you do have to tighten it pretty good. It feels a little bit more than I would have expected when I first started doing it. But it's easy enough to verify. Just touch the side of the probe, and if the probe moves, which this one did move a little bit, I need to tighten it a little more. So I'm just going to crank that down a little bit more. And now it's not moving, so I'm good. All right, so everybody take a look at that, and you can see again the probe is in the upper half of that. That's where it needs to be. Yeah, you could use that. Yeah, if you can't see it, then you can use that. I have one of these in my lab. These are really nice. Once you get used to loading probes, you find it's really easy, and you find the first few times you do it, you're going to be shaking and breaking tips and stuff. I would recommend taking an old tip, like the one I just dropped. These tweezers are not really good. If I can find another pair of tweezers, I'll give them to you. These are a little too stiff. And so you want tweezers that really don't have a lot of spring in them, because you don't need to push hard. If it has too much spring, you tend to shatter the chip and drop silicon dust all over your tip holder, and that's not good. So these are not ideal. Good? Alright, so then once we have that, just pull this out. We're going to bring it over to the AFM. Okay. So, just like on the other on the little black stand over there, there's a little lever that you have to press. Okay. You push that lever, and you'll notice on the tip holder you have a dimple, and then on the other side 2 slots. Okay, so that's a kinematic mounting. It prevents rotation in both directions, and it prevents, well, basically it limits all 6 degrees of freedom. Okay? The part that you're pushing has to line up with the dimple. Right? That's the same size as a clip, right? So you take the clip, the probe clip, and you line it up with that. Then you're going to push this down, slide it into place, and lock it in. If it moves, it's wrong. If it doesn't move, it's right. There's no in between, right? So if you reach and you try to twist this and move it around, if it twists and moves around, then something's wrong. You did something wrong. I recommend, in general, always using 3 fingers, right? Because you have a tendency when you use 2 fingers when you pull it out, especially on that one where it's stiff, people will come up here and they'll do that, right? Whereas if you use 3 fingers, right, you can't do that. Well, yes, you can. If you use 3 fingers, you won't do that. Yeah, it's fine. It's different here than there. This one's a little bit bigger, but yeah. In general, 3 fingers is better. Okay, so now we load the sample. Make sure that this is all the way down. Magnets to hold it down. Strictly speaking, they aren't necessary. There's enough friction between here and here to keep it straight, but you know, we recommend using them. Okay, so this now, 3 fingers. Push that in. Now, same thing. I took the head and I just moved it that way. I want to take the shortest route back. I don't want to flip it this way. I want to flip it straight over. Okay? If you're uncomfortable with that, you can take it and straight over this way and set it here. Then get yourself prepared and then slide it over. Again, you're holding here and here. That's the safe place to grab it. Now, when you put this in here, you don't really know how big the last sample was. Right? I've put the 2 back feet in there. If I just slam this down, if somebody had a taller sample than I do, I just smashed my tip.
Yeah.
You're not going to hurt the AFM, but you can smash your tip. So what I want to do is I want to look sideways down here, and as I bring it down, I want to watch it. And if it looks like it's going to hit, then I'm going to take this and spin this up. If that's still not enough, that looks okay. If that's still not enough, then I want to lift it back over here, put those in place, and I want to raise these up. So let me take a pause here and walk you through what these buttons are, or what these controls are on here. Okay? There are 9 adjustments that you can make on this. The 3 simple ones, let's see if she can make sure we can see. The simplest to see and understand are the legs, right? There's a knob here, here, and here. All 3 control a leg. Each one controls a single leg. That means the head can be tilted in various ways. That can be good or bad. If you have a weird sample, or if you have a really short tip, it's sometimes nice to tilt the head in the direction to help the tip. But if you exaggerate that too much, you can hit the clip first, or you can hit the some part of the sample first. So you want to be a little careful. Only tilt the head if you're doing it on purpose. If you're doing it accidentally, it's probably going to go wrong. Okay? The way to understand which direction it moves is you look at the little arrow on the top. It says up, and then it has a curved arrow like this. That means that if I take this knob and rotate it along the arrow, I'm raising the head up. Think of it as a circle all the way around. Okay? If I turn this, 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 I'm pulling all 3 legs up. In general, once you have things set up, if the image of the tip is staying in the center of the camera, it means you're going straight up and down. If the image is moving away from the center of the camera, it means you're tilting it. Right? It's okay to have a little bit of tilt, but it's not okay to have an extreme tilt. And you never want to have the back, I'm calling this the back, or the left side, lower than the right. Because if you look under there, that's where the clip is. And so if I take this thing and lower it all the way down, I'm going to hit the clip before I hit the tip, and it's going to fail. Does that make sense?
Mm-hmm.
All right, so then the next knobs, so you got legs. The next knobs are called LDY and LDX. LD stands for laser diode. It's actually a superluminescent diode, so I guess it stands for luminescent diode. But it's basically it's a laser without the cavity. All right, so it gives you a little bit of a broader spectrum of wavelengths. They center around 860, I think 860, yeah. And these two adjust the position of that laser. Again, we've included a graphic that's meant to be helpful to you. This is supposed to represent the orientation of the probe, right? I showed you guys a minute ago the clip is down on this side, the probe sticks out from that side, right? This knob on this side now corresponds to this graphic. This knob down here corresponds to this graphic, right? It is exactly the way you're looking at it. The probe is here. This says to me that if I rotate this knob away from me, I'm moving the laser spot away from the probe. This one says if I move this knob to the left, I'm moving the laser spot up relative to where the probe is. Using this, you can almost always find the cantilever. If you walk up to the system and no matter what you do, you can't see the laser, you take one of these and go all the way to one side, count the number of times it takes to go to the other side, go back to the middle. Take the next one, go all the way to one side, count the number of times to go to the opposite side, go halfway back. It will be in the exact middle of that glass that I showed you. The little parallel, no, it's a trapezoid. Okay, sort of trapezoid. Okay, so legs, laser. Obviously, it goes without saying that once you have aligned the laser on the back of the cantilever, you have to align the reflected beam, right? That's what the PD knob does, right? It stands for photodetector. Very simple. If you look on the sum and deflection meter and you see a negative number, I'll show you in a minute, you go towards a positive. If you look at the sum and deflection meter and see a positive number, you move this towards the negative. Even if you're moving it and it's not moving on the meter, just keep going. Eventually it should work. If you go so far that the sum starts trailing off, that means you started all the way at the opposite extreme and you need to go back the other extreme. But 99% of the time it will align unless there's something really wrong with your probe. Okay? Alright, so that's 6 of the knobs, the 6 of the controls. 2 more controls are these 2 knobs right here. These adjust the tilt mirror in this optics, which this is the camera that you use to look down onto your sample surface. This right here aligns with this, so when you look down, it looks down here, over, and down onto your sample. This adjusts where you're looking relative to the tip. So, in general, this should be roughly centered so that when you look down, it looks like it's looking straight down. I've done alignments where I'll take something like this and put under it and then illuminate it, and then I'll adjust these until I can clearly see that, and generally that will help you with gross alignment. If somebody completely messes that up, you can usually look in there and it's obvious because the mirror is going to be off at some strange looking angle. You should be able to clearly see where the tip is by looking straight down, right? As long as nobody changes this by very much, it shouldn't be an issue. The other control that you have is this ring right here, this brass ring. And this is a little tricky to move. Some people find it uncomfortable. This one actually seems in pretty good shape. This adjusts the focus of the objective lens. The objective lens is right here, right? And so what it's doing is it's moving that back and forward in order to get the focus. Okay? I know I lifted it up wrong, but I have Kung Fu grip. Alright. I keep hitting my head here while I'm holding the AFM, almost dropping it. Okay, so I'm going to come over here, put the back feet in again, look down sideways, make sure it's clear, It's clear. Right? Generally with this particular stage top, this is a little bit older, a stage top. If you're now and then possibly later when you're done with your experiment, what I recommend is just putting your hand on top and just kind of moving back and forth, because that's going to put it at its relative minimum. I've seen situations where I don't do that, and while you're imaging you can get a little tiny bit of drift that's unexpected. So just put your hand on it and just kind of move back and forth, right? Just almost like you're just pushing and doing that, okay? It's not strictly speaking necessary, but it's decent. So then now what I'm going to do is I'm going to make sure that my tip and my sample are aligned. That doesn't look like there's a tip in there. That's weird. Oh, it's there. Okay. Looked like the tip had fallen out. Okay. So now, looking at this sort of macro, what I'm going to do is I'm going to bring this down manually, sort of keeping an eye out for tilt. Now again, a little bit of tilt in this direction is okay. A tilt in this direction is bad, right? So it looks like I have a very slight tilt down here, so that's okay. So I'm just going to bring it down, bring them all together until it's really close. And when I feel comfortable that I'm close, right, then I can come over here and look in the camera. Now, in this case, I'm looking through here through this window because it's more convenient. Sometimes people will have this closed and they'll look directly. But what I'm looking at is I'm looking at the camera. In order to get the laser aligned properly onto the back of the cantilever, I need to be able to see it in a camera. Now, strictly speaking, that's not true. You could use this if you wanted to, but it's a pain in the ass. Right? So I recommend using the camera. That makes life much more simple. Okay? So I'm looking over there. Now if you recall, what I showed you guys when you moved it around was like a little trapezoid. Right? Well, that trapezoid should be hit on that camera, should be showing this way. Because when you look here, that's where the trapezoid is. So it all lines up together. When I look at that image, I see a line where it's bright and then it's dark. That leads me to believe that that's probably the trapezoid, right? Because there's light coming through the region that I told you was active, and there's no light coming through the region that I told you was not active, okay? So what I'm going to do is I'm going to assume the probe is going to be down here somewhere where I told you guys I should load it. So I'm going to play with that camera, and I'm carefully going to watch that, and I'm going to see which axis is the right one, and sure enough, there's my probe. Okay, and I'm going to move it until the probe and the substrate take up most of the image. Later on, I'm going to move it out of the way so that I can see the sample. But right now, I'm trying to align my laser, and I want this part of the cantilever of the probe to be visible, so that when I put my laser spot over here, I can see it. Then I can align it onto the cantilever. Okay, so I don't see anything right now that looks like the laser. So that tells me that the laser is probably out here, although I do see something right here. All right, so that might be it. And sometimes turning down the light will help it show up better. Now you can see, oh yeah, look, there is something that's probably the laser right there. So in order to find it, I'm going to move it over here because this is a nice big flat area that's at the right angle. So I'm going to move it that way. So I come back over here, I look at my little label here, my graphic, and I say, all right, well, I think if I go that way, and there it is.
Yeah.
So if it's the right spot, there are ghosts, right? I call them ghosts. See that spot? Yeah, see that spot right there? Mm-hmm. That looks like the laser too, right? How do I know it's not the laser? There's no sum, right? There's no sum. So on the reflected signal to the photodetector, it's a 4-quadrant photodetector, but right now we only care about 2. So just imagine the upper and lower part across that line. If I am anywhere on that, right, I should see A plus B. In other words, whether it's here, 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 doesn't matter. My sum should be maximized, right? If that really is the laser spot, I should be getting a lot of reflection on here. I'm not. So that tells me that's not the spot. And it turns out that little ghost is always up north of the actual spot. It's always higher. So if I see that, I know I got to move it up so that I can bring the other one into view. And now you
it's
can
5
see
point something.
exactly. So now I have 5.4 volts or whatever it is reflection. But again, that's A plus B. If A is the top and B is the bottom, that's A plus B. This is A minus B.
Yeah.
Right? And you can see from this that sitting here, it's -5. So going back to what I said before, I would have to move that towards the plus once I'm aligned. But we're not there yet. Okay? So now what I've got to do is, now that I've got it roughly aligned up and down, is I've got to move it out to the probe. Now it's going to disappear for a minute right there, because that part of the cantilever holder, you can even almost see the line, of the probe, this is flat, but this is beveled down. So the light that's coming from there is getting sent off into a direction that the camera can't see. Right? So that light's gone for now. But I'm going to keep going, and it should reappear. So I keep going, and there it is. So now I've got to go up and down to maximize the sum.
10. 4.
Okay?
Yep.
And now you can see that's the maximum sum I'm going to get out of this. That's a bit low. Okay, so typically you want to be between 6 and 8.
Okay.
So this tells me that something's not right. What I think is not right is I believe that your window has been scratched up. So these silicon probes are pretty hard, and they've got silicon dioxide on them. And so over the years, as people use these things and drop levers and smash tips and do that, you just get these tiny little scratches that appear on there. It's going to get worse over time. So at some point, I'll test it either now or either today or tomorrow with one of my holders and see if with the same probe I get a higher sum. In which case I'll have to recommend that she get it fixed. But this is functional. 5 volts is fine. It just means your optical lever sensitivity, in other words, the sensitivity of the cantilever itself, is going to be about half of what it normally would be, right? Because it's proportional to the sum, right? So if I had 8 volts, I would have much better optical lever sensitivity. Okay? So that's the best sum I can get for now. So I'm going to go with that. And now look at the deflection. The deflection is at -10. So I need to come over here to the photodetector, and I need to move this towards the positive until I can get it close to 0.
Yeah.
It does not have to be exactly 0, especially if you're doing tapping mode. If you're doing contact mode, you got to be a little more careful with it. Typically, people will put it to a very small negative number, like maybe -0.2, -0.5, right? We can get to that later. But if you're doing tapping mode, which is what I'm teaching you now, because it's 90% of what gets done, you want to be close to 0, but don't stress yourself out trying to force it to be exactly 0. It's just a waste of your time. As long as it's between plus or minus 2 volts, the oscillation is very linear and very reproducible. So a little bit of an offset is no big deal. Okay? So even though I obsessively made it 0. So, all right. So now that we've got that set up, I need to come back over the software because I have to characterize this probe. Right now, I don't have any significant amplitude, so I can't get the tip on the surface. Right? If you recall from Chris's talk, we're going to oscillate the cantilever at its resonance, and then we're going to slowly lower it down until it starts hitting the surface. Right? Once it reaches the set point that we've given it, right, it's going to beep at us and it's going to say, okay, I found the surface. The system doesn't actually know if it found it, it just knows it reached the set point. So you've got to be clever enough to make sure you know it's on the surface. But in order to get it on the surface, I need some free amplitude. So I need to know what the resonance frequency is. It's also helpful to know what the spring constant is and what the optical lever sensitivity is. I'll explain that a little more as we go along. Okay? So to do that, we have a little automated routine that's called Get Real. So I'm going to go to thermal tab. So I'm now, I don't know how many people can see. I'm going to sit down so I'm out of the way. The view. All right. So now if you look over here on this master panel, okay, if I look under thermal, there's a button that says Get Real. I know it's kind of a lame marketing term, but it's a good technique. It's effective. It's based on John Sater's 2020 or 2012 article describing how to use, it's a variation of it. Basically, you can use a database in order to get the spring constant and optical lever sensitivity of a certain class of probes. Now, in general, there's one kind of major issue with this, and that is everybody has their own names for probes. So if you buy a probe from Nanosensors or Brooker or Asylum or various people out there, everybody has different names. And so you might look on here, look at your label like I'm doing now, right? I look at my label and it says Asylec 1. And I look over here and there's no Asylec 1 on here, right? But more than likely this probe is on there. It's just a modification of that, or it's a different probe. So if you run into a probe where it's not on there, put a question into support, put a question into the forum, ask me, and we can probably help you cross-reference it. This particular probe happens to actually be what's called an FM, which stands for frequency modulation. It's a historical name. Don't worry about it. It's just the way it is. The newest version of 16 does a much better job of listing the different probes and different brands and stuff like that. Like for example, this has a little bit of it, but FM here is actually the same thing as Econo FESP. Those are the exact same probes. It's just that they're called FM by Nanosensors and they're called FESP by Brooker. And so we put them in there, right? That detail, if you can't find it and you don't get an answer from us, you can always put in a generic value, which is better than nothing. If you look down at the bottom, you can just enter the dimensions of your probe and the approximate spring constant, and it'll come up with an estimate that's going to be relatively close. Okay? When you're done with that, when you're done selecting, you click Get Real. And now it's going to look, you see it found it right away, and it's going to do a series of thermal tunes. What a thermal tune is, just passively looking at the oscillation of the cantilever, which is of course going to be at its resonance. Everything is always moving at its resonance if it's not at 0 degrees Kelvin, right? And so from that we can find the resonance peak, fit it, and then backtrack out what the spring constant and optical lever sensitivity is approximately. Okay. There. So it finished when the little green bar at the bottom is done. It means it's done. Okay. Now you can tune the cantilever. So I can right click on it, somewhere near the middle, and I'm going to press move frequency, phase, and amp to tune. Okay? It's a bit cryptic, but what we did was we did a thermal tune in order to find the resonance and characterize the probe. We now want to do a mechanical tune. Now we want to actively drive it because we need a big enough amplitude to tap the surface. So we must actively drive it. This is setting that up. So I'm going to go move frequency, phase, and amp to tune. It's going to switch over to the tune tab automatically, and it's going to do a sweep and tune the cantilever at its resonance. Right? If for some reason you want to look at it, you can go under graph and you can append the thermal. That's the thermal tune I just took, the red dotted lines. This is the mechanical drive. You can see that they're slightly different. That makes sense because mechanical drives are inherently dirty, right? You are driving something which is driving something else, which is driving something else, and you're going to get some error, some slop in there, okay? So, but that should be okay. Generally though, I like to put it right on the peak, so I'll hit set drive frequency right on the peak, okay? And then I'll usually center the phase. Okay, so now I've got my cantilever tuned. If you notice, the amplitude now, instead of being a few millivolts, is now 1 volt. For the approach, for putting the tip on the surface, I recommend a volt as your free amplitude, and I recommend 700 millivolts or 0.7 volts as your set point. So that's scalable. So if you want to use 2 volts as your free air amplitude, use 1.5-ish as your set point. If you want to use 3 volts as your free amplitude, use use 2-ish, right? 2 volt set point. You want to keep that ratio roughly the same though. That makes sure that you're going to actually